All right, let's talk about something really cool. Imagine you're watching a vertical laser beam scan across a city skyline. Now, every single time that beam hits the edge of a building, either the beginning or the end, something important changes, right? Well, that's the big idea behind one of the most elegant and frankly beautiful techniques in computational geometry, the line sweep algorithm. So if you're a developer or you're deep in your CS studies, you've definitely run into this. How do you actually deal with a whole mess of overlapping rectangles or intersecting lines, all scattered across the 2D plane? I mean, the first thought is probably to just check every shape against every other shape, which, as you know, would be incredibly slow. We're talking painfully slow. Well, here's the brilliant trick. You don't have to do that at all. The line sweep algorithm lets you transform that messy, two-dimensional chaos into a beautifully simple, one-dimensional sequence of events. And that right there is a huge shift in perspective that makes these seemingly impossible problems suddenly very, very manageable.
Okay, so let's really dig into this core concept, the sweeping line. This is where we take this entire complex plane and just reduce our focus down to a single moving line.
So here's the textbook definition, but let's break it down. A line sweep is an event-driven technique, and that phrase is absolutely key. Our sweep line doesn't just move smoothly like some animation. No, instead, it instantly jumps from one critical point to the next. And we call these critical points events. And this is the light bulb moment, the fundamental mindset shift you have to make. Think about it. The overall state of our problem, like how many rectangles are currently overlapping, it doesn't change in all that empty space between the shapes. The only places where the answer can possibly change are at the exact coordinates where a shape begins or ends. So that means we only have to do our work at these specific discrete event points.
So how do we actually pull this off? What's the machinery behind it? Well, to make the sweep work, we really just need two key components: a way to manage all of our events, and this other thing we call an active set.
And the process, you'll find, is almost always the same 3 steps. It's like a recipe. First, you look at your problem, at your shapes, and you define what your events are. For simple intervals, it's just the start and end points. For rectangles, it's the left and right edges. Step 2, you collect all these events into one big list, and you sort them. This sorting step, by the way, is why these algorithms are so often O of n log n. And finally, step 3, you just loop through your sorted events one by one. And at each stop, you update a data structure that keeps track of what's currently active, what's currently crossing your sweep line. And that's your active set. So let's just pause for a second and appreciate this transformation. We are taking this complex, continuous, kind of scary 2D plane, which is really hard to deal with in code, and we're boiling it down into a simple, discrete 1D sequence of events that we can just loop through. It's such a powerful simplification. Okay, that's enough theory. Let's get our hands dirty and see how this powerful idea actually cracks some classic problems, the kind you are definitely going to see in coding interviews. First up, a classic, finding the maximum overlap of intervals. This is the exact problem that powers questions like Meeting Rooms 2 on LeetCode. The goal is simple: find the maximum number of meetings happening at any single point in time. All right, let's walk through it. Our sweep line starts moving from left to right. Boom, it hits the start of our first interval. We process this start event and our overlap counter just clicks up to 1. Simple. Okay, the line keeps going, and now it hits the start of a second interval. We process that event, our counter goes up again, this time to 2, and we make a note. 2 is our new maximum so far. And finally, our sweep line reaches the end of that first interval. This is an end event, so what do? We just decrement our counter back down to 1. And that's it. By the time we've processed all the start and end points, the highest number our counter ever hit is our final answer. Now, let's level up. What about finding the total area of a bunch of overlapping rectangles? A simple counter is not going to cut it here. Why? Because between any two events, we need to calculate an actual area. And that area is the distance between the events on the x-axis times the total vertical length of all the rectangles that are currently active. So our active set needs to be smarter now. It can't just count. It has to track and merge these vertical line segments. So how do we handle this? Well, we break down each rectangle into 2 events. We get a start event at its left edge, we can call that a +1 event, and an end event at its right edge, a -1. Each event holds its x-coordinate, its type, +1 or -1, and the y-interval of that edge. Then, we sort all of these events by their x-coordinate. Now, between any two of these x events, the active vertical cross-section is constant. So we can just calculate the area of that little strip and add it to our running total. Implementing the basic idea is one thing, but getting it right, especially in a high-pressure situation like an interview, means you have to master the details and the edge cases. This is what really separates a good solution from a great one. And these are the classic traps you have got to watch out for. Are your intervals inclusive or exclusive? Because that choice changes everything. What happens if two events are at the exact same coordinate? Say a meeting ends at the same time another one starts. Which one do you process first? Are you thinking about weird cases like zero-area rectangles? Or what about the nightmare of floating point precision errors? You have to be super precise about all this. And honestly, this is the single most critical detail of them all, the tie-breaking rule. Let's go back to the meeting rooms problem. If one meeting ends at 10 a.m. and another one starts right at 10 a.m., you absolutely want to process the end event first to free up that room, right? Your sorting rule has to enforce that logic, or your answer will be wrong. So let's put this all together. How do you present this whole approach in a way that's really going to impress an interviewer and, land you the job? This table right here is basically your interview study guide for line sweep. For max overlap, a simple counter, or maybe a min heap works perfectly. But for that rectangle union area problem, you need a more powerful tool for your active set, something like a segment tree. Why? Because it can efficiently calculate the total length of a union of vertical intervals, which is exactly what that problem needs. Then for finding all k-intersections between line segments, the active set has to be even fancier, usually a balanced binary search tree. But notice, despite the different data structures, the time complexity is almost always dominated by that initial O and log n sorting step. Okay, if you take one thing away from this for your next interview, let it be this. When you get a geometry problem that smells like a line sweep, do not just jump into coding. Take a breath and state your plan out loud. Say, okay, I think I can solve this with a line sweep. My events will be the left and right edges. My critical type-breaking rule is to handle start events before end events. And for my active set, I'm going to use a segment tree. You see? This shows a clear, structured thought process before you've even written a single line of code. It's a game changer. At its heart, line sweep is all about reducing dimensionality. We took a tricky 2D problem and we solved it in 1D. And that leaves us with a final, really fascinating thought. What if you applied this idea again? What if you had a 3D problem and you tried to solve it by sweeping a 2D plane through it? What kind of even harder problems could that unlock? Definitely something to think about.